Well, hello everyone. I guess not many people are coming here today. Yeah, so the idea of today's lab is three things. First of all, I will give you a very short introduction to BIM, in case you haven't had the time to go through the materials for the lesson. Then I will explain to you what you need to do for homework assignment number 3. I know that a lot of you are still working on homework number 2, though. And in about 45 minutes, Hugo will be here also to answer questions about homework assignment number 2. And I will stay here to, if in case you have any questions about the lessons. Yeah, in order to explain to you what BIM is, I think it's best if we just have a quick practical look. You have already been seeing many examples of 3D city models, I think. So I will just open a few of them and maybe we can start the discussion from there. Like here. This is an example 3D city model made by the city of The Hague. You can see a bunch of buildings. This is like one neighborhood. If you go to any one of the buildings, you can see that maybe it's either a separate building or it's composed of building parts. It has some attributes, in this case like roof types, height of the eaves of the roof, height of the ridge of the roof, and so on. This is a model with not that much detail, as you can see. Let me open another example. This is another 3D city model example. Here you can see the faculty. Yeah, so there are some similarities to what you saw before. There's a building. In this case, it's an excerpt from the 3D bath that you might be familiar with because you might have been using it for homework assignment number 2. Yeah, it's a similar thing. You have buildings, building parts. You have all the attributes that you know from homework number 2. As opposed to the previous model, you can see that it has a bit more, quite a bit more detail. This is something like an LOD2 model, so it has a different height for the roofs and more complex shapes. And let me open one final example, maybe something quite a bit bigger. Okay, this will take a while. Yeah, so this example that you're about to see, it's a 3D city model from the city of Vienna. It's actually the entire city of Vienna, modeled in LOD2. This was, no, sorry, it's an example from the city of Zurich. It's a model that I think was created by ETH, covering all of the city. Sorry, the computer is struggling a bit since I'm trying to open this and stream and everything. So yeah, here you can see the entire city of Zurich. If we open an example here, like a building part, this corresponds to part of the building of the train station, the main station in Zurich. You can see that it has a bunch of attributes for the building. It's composed of building parts. And very importantly, that it tries to cover a large area, in this case, the whole city of Zurich. So Next, I want to open some examples of IFC models. And yeah, hopefully you can tell me a bit like what is the difference in what you can see here. So how does a model like this one differ from the 3D city models that you know from the previous lessons and what you saw just before? Yeah, it's a lot more detailed. Here you can see much more detailed shapes. You can see individual windows, doors, like the entire shape of the roof with a balcony and so on. Anything else? Yeah. Usually with 3D city models, we don't cover the interior. In theory, with CityGML, it's possible to do it with LOD4, but at least it's not a priority, right? Anything else? Yeah. So for instance, if we open one example here, this is sort of a wall on the roof of the building. It comes with a whole bunch of attributes for the semantics, like the name of the wall, what kind of wall, the material. And if we open something else, like a window, we also get a similar description of each element. Let me open something very, very different. So here is something that doesn't look at all like a 3D city model, because BIM not only covers buildings, which is sort of where 3D city models and BIM overlap, but it can also cover things like ventilation and heating, utilities like pipes, for sewage, for water supply, and so on. And even things that also have nothing to do with the usual 3D city model. So everything that's related to infrastructure, so even temporary things like the construction cranes can be modeled in BIM and in IFC. And these have sort of the same kind of detail that you see elsewhere, right? So it has a set of materials, like in this case it says that the crane is made of steel. Yeah, so if you just get a superficial look at both kinds of models, there's a lot of overlap, mainly when it comes to buildings, but there are actually quite a few differences, and I want to summarize this a little bit more. Yeah. So BIM, to be clear, is not only about the BIM models, which is the most important things for us in geomatics, but BIM refers to an entire methodology. So when people that are not in our field talk about BIM, they're not only talking about 3D models, they're talking about a methodology that is used like on how buildings are designed, like maybe an architect or designer starts from a very rough shape, like the plot of land where a building is supposed to fit, and then it creates like the volumetric representation, so simple forms. Then it starts to have a lot more detail, starts to define like what kind of building elements you need in order to be able to construct it. Then a building is built. Then maybe you want to use the BIM model to do maintenance, to manage the facility, like what rooms are available. Whenever you need to do some remodeling work, you know what materials are there. You know what kind of insulation it has, like for heating. So BIM is a methodology, not only the 3D models that are used for them, but this methodology involves creating and using very detailed 3D models of buildings. Not the sort of thing that you see with the 3D city models, where a lot of the time one building is just one simple shape. This covered both geometry and semantics, so detailed geometry and detailed semantics. So you have semantics for every single building object. Like if there's a column, you might have semantics only for that column. If there's a window, you might have semantics for the window. So maybe like what kind of thickness, what kind of glass it is using, and so on. BIM covers not only buildings, but it covers infrastructure projects as well. There's a lot of construction going on. So if people want to build something like a train line or a road or a bridge, this is covered by BIM. And the idea is that it can be used in design and construction. This is more or less the current use of BIM. But in the future, people want to extend it to all sorts of things. Like in our research group, we have been discussing a bit how this works with building permits. So the future all across Europe is more or less that an architect or designer creates a BIM model and submits it to a government portal. And then the people in the government can do all sorts of checks on it to make sure that it satisfies all the requirements. Simple things like zoning, but also much more complex things like how it complies with evacuation plans, whether it's wheelchair accessible, and so on. All of this can be checked from the BIM model. And in the theory, in the future, it should be possible to do that, preferably with automated tools. So if we do more or less a comparison of how BIM and 3D city models stand, these are the main differences. So in terms of origin, BIM comes much more from the architecture world and the computer-aided design world, whereas the GEO world, so 3D city model, comes more from cartography and maps. One thing that you could have mentioned before is that BIM only covers one building site, so either one actual building or a site where a few buildings or an infrastructure project are located, whereas 3D city models cover large regions. When you make a BIM model, you create it manually based on the design. So from the design plans, there's a person who sits behind the computer and sort of starts designing all parts of the building. And with 3D city models, usually you start by measuring things. So there's already something there. You take some measurements, and from there you start creating the model. I will talk about the volumetric and semantic surfaces a bit later with an example. BIM models are not so much up to date in the sense that they are created usually when a building is designed. And sometimes, especially for large projects, this model is updated based on how it was actually built. So there are slight differences between the two. But yeah, there's always a BIM model when it's designed, sometimes also when it's building is built. 3D city models are based instead of on whatever is the input data. So like in the 3D BAH, it starts from what is cadastral data, and then also from point clouds, like from AHN. And then it's up to date based on when the source data was updated. Yeah. With BIM, the focus is on buildings and infrastructure. With 3D city models, is basically everything. But it's mainly focused on cities, so more urban areas than rural areas. But it also covers things that are not covered in BIM, such as water bodies, vegetation, land use, and so on. And yeah, it comes with different strengths. So BIM is used a lot in design and construction, but with 3D city models, you can do much more wide things. So the kind of big spatial analysis that are not possible to do only with one building. What I skipped previously is more related to how actual geometries are represented. So in BIM, that is very strongly tied to construction. You care about the building object that actually takes space. So if you need to build a column, or you need to build a wall, or you need to build a floor with a slab, all of these things are explicitly modeled as objects in BIM. But in the GEO world, we don't care so much about that. We care more about the empty space between. So maybe between this floor and these walls and these windows, we have a room. and we care more about the surface, the actual visible surface from us of the room, and how we can use it. So in this figure here, you can sort of see these two conceptual views of the world. So BIM more or less covers the middle example, where you have volumetric walls, so the walls occupy space. And in the left-hand example, you can see more or less the geo view, so the GIS view, where you only care about the visible surface of the wall, so the stuff that we can see, like from being inside of the house or inside of the room. And for these surfaces, we label them based on the semantics. So we don't see a volumetric door, we just see the surface of the door that is visible to us from there. Yeah, so this more or less leads me to what you need to do for homework assignment number 3. Because in homework assignment number 3, you need to do BIM to geo conversion. The idea is that you will start with a BIM model in IFC, and you will do some basic processes in order to be able to convert it to a CityJSON model. The purpose of doing something like this is that maybe you already have an IFC model that was created by architects because they are building something new, and you want to incorporate it into an existing 3D city model, maybe because you want to run some analysis there. Yeah, the rules for the assignment are similar to those before. So you are allowed to work in a group of 3. You can keep the same groups that you had before. Yeah, you can also work in pairs or as one person, but we don't recommend it. It's quite complex what you have to do for this. And the assignment is worth 20% of your final mark. Yeah, so this is one more of an example of an IFC file. I just hid the roof from there so that you can sort of see the different rooms that are visible there. When you do the BIM to geo conversion, more or less you need to extract the outer surface of the building, plus the inner surfaces corresponding to each room in the building. Yeah, the recommendation is to go for something of more or less this complexity, so don't go for a huge high-rise building. It's going to be very difficult. But I will give you some more tips about this in the instructions. So let's go through the steps that you need to do here. There are 5 steps. I will just discuss them more or less one by one. So yeah, it's a programming assignment. You need to do this in C++. And hopefully in the very first part of the course, you did homework number 0, which involved installing Seagull and making sure that it was working. Now is the time when we actually use this library. You can also use any other external libraries, but this can only be used for reading and writing files. In particular, you need to write a JSON file at the end for CityJSON, and for this you can use any JSON writing library. There are some suggestions here. And yeah, so how to get started? This is the final assignment of the course, so we provided you with a bit less help. There's no sample code for you to use or a skeleton. You are free to structure your code in whatever form you like. But we have provided a lot of code snippets for the most difficult things, and these are inside the assignment description. So it's up to you to take these small pieces of code and to put them together into something workable and to fill the remaining gaps. So to start developing your code, I think it's really best if you start with a very, very simple IFC file, because IFC files can be very complex and very large, so start with something minimal. There's a file link there that is called the IFC Open House. Let me show it to you. So yeah, this is a very, very simple IFC model. It's not an actual house. It's a one of the earliest examples of an open IFC model that you can find on the internet. Basically, since BIM is dominated by industry, there's a lot of proprietary information and people are not very willing to share IFC models so openly. So in order to be able to solve that, a researcher at the University of Eindhoven basically created this very simple model. It's something very small, so it's just a house on a hill. You can see that there's nothing below the hill. The house sort of has this foundation, a wall, a bunch of windows, and a roof. There's a door on this side, but it's just made of very few elements, and this is good in order to be able to debug your code. And yeah, you can already see it sort of from the window, but there's basically one single inner room here. So if you wanted to achieve the results of the homework 3 assignment, you basically need to extract the outer surface of the house and the inner surface that corresponds to the room inside the house. But something simple like this is only good for starting up and debugging. The main idea is that you need to create BIM to Geo conversion of one somewhat more complex building. It is up to you to choose one. There's a link here that links to a repository of open IFC files. Just pick something in there. Don't go for a high-rise building or something too complex. Pick something that is kind of simple, so like the duplex apartment that I put there in the beginning, or one of the models that are labeled KIT, like for the Karlsruhe Institute of Technology. These are relatively simple, but already provide enough of a challenge for the homework assignment. So just go to the open IFC model repository and start downloading a bunch of them. Pick something that you will like. How do you open an IFC file? There are a bunch of open source or free viewers. Yeah, out of the ones that are free, I think the most reliable one is Solibri Anywhere. For that one, you need to register in their website. And the viewer is a bit clunky, but it works fine. It displays all objects, unlike some of the other options. There's the Open IFC Viewer. This is a much newer program that is specifically open source. This is also meant to open very large files, and it's free. You don't need to register, but you might have some issues viewing some elements. So for instance, if you open the Open IFC house, or IFC Open House in the Open IFC Viewer, you might not see the door because it was modeled in a slightly non-standard way. And yeah, some of you are already familiar with Blender. So Blender is this 3D modeling software that you can use to create nice renders, and it's open source and partially made by people here in the Netherlands. So it's very good software. And there's a Blender BIM add-on that it's very easy to install. So if you install that add-on, you can open IFC files inside Blender, and you can create very nice renders for them. So yeah, install one of these, browse through the models in the Open IFC model repository, and choose something nice. But yeah, indeed, start with something very simple to develop your code. After that, in the homework page, there's a bit of a general Seagull help. Seagull is difficult to use and difficult to get started with. Yeah, it uses a lot of advanced C++ features that I don't think you covered in the C++ part of the programming course. There's like a lot of templating and different types. So there are some suggestion headers. If you can just include this in the beginning of the file, you will more or less get what you need. And after you put the include definitions, you can put these Typedefs. Basically, what these do is that instead of having to write this whole thing like Seagull colon, polyhedron, _3, and between pointy brackets kernel, you can just write polyhedron. So these are not necessary, but they allow you to keep your code much shorter and much more readable. So, and this is using actually the kernel that is defined here. So these are not necessary, but they will simplify your life quite a bit, because otherwise you will also get like gigantic error messages with Seagull. Yeah, also to get started, it would be great if you go to the Seagull website and check the documentation for how to use the basic structures that you will use. So these are the points, the polyhedron 3 and the polyhedron 3. Let me explain to you a bit how this works. Like if you click on the link that I put there, you will go to the Seagull documentation, and in here you will find two manuals. There's a user manual and a reference manual. In the user manual, there's basically a description of the whole package, so how this works, so what sort of data structure it's using inside. And there's a bunch of sample code, so these sort of small things that tell you how you can actually use the code. Basically, if you just copy and paste these small pieces of code, you should be able to run the programs. And that's also how you can make sure that everything is working fine in Seagull. So yeah, in order to understand the Seagull package, go through the user manual. And if you go to the left, you will also see the reference manual here. And then, yeah, you can get all the detailed information, like for instance, if there's a polyhedron 3, and you want to know all the functions that it has available. Yeah, they're all described here on this website, and each one of these comes with a description. Some of them come with examples and so on. The Seagull documentation is very good, even though the use of it is quite difficult. So yeah, don't be afraid to go to the documentation. Yeah, this was also part of the homework assignment number 0. So in order to compile code that uses Seagull or any other external library for C++, you need to do a few things. Mainly, if you go to your CLion installation or whatever you're using, if you go to the CMake lists file, you will have something like this. Is this readable? There are two important things that you need to add. This find package, Seagull. If you add that to your CMake lists, it will find whether you have Seagull installed or not. And it will define a bunch of variables that tell CLion how to compile your code. And then this one include Seagull use file. Yeah, after the small script it finds where you have Seagull installed, this actually tells the CLion compiler how to compile all the headers. So where the headers are located. What I'm showing you here is a slightly more complex. You're free to use this if you want. So this small piece of code in the CMake list is basically trying to find Seagull. Then if Seagull is found, it includes it, and it gives you a message saying Seagull found. Otherwise, it will send an error saying that this code requires the Seagull library, and it stops. Something like this can help you in order to know that you actually have Seagull working correctly in your computer. Anyway, let's go through the steps that you need to do for the homework assignment number 3. Since reading IFC files is very, very complex and we have limited time in the assignment, the first step that you will do is converting the IFC file to OBJ, because you have already worked a lot with OBJs and maybe you already have some nice code to read and parse them, and it would be great if you can reuse that. So for this, you should use IFC convert. IFC convert is part of the IFC OpenShell library. And there are binaries for Linux, Mac, and Windows, so it shouldn't be a problem. Yeah, using this, you can basically go from IFC directly to OBJ. So, for instance, from this IFC file for the duplex house that is in the description of the homework assignment, you can go to something like this that you can open in MeshLab, like in any other OBJ file. And the idea is that you will not start directly from IFC, so you will start from this OBJ file, which is a simple text file that is easy to read. But yeah, IFC Convert has a bunch of options. If you run it through the help option of IFC Convert, you will see what these are. Let me do that for you here. So yeah, if you just run IFC Convert like this, it will give you sort of how to use it. But then if you just run IFC Convert and then you put also the help option, it will tell you all the different options that it has. There are some relevant ones. There's this include and exclude argument. There are options to only extract some of the objects or some of the objects in the IFC file and so on. And this is important because if you just extract everything in the IFC file, it's going to be very large and very complex to extract things. So ideally, what I would suggest is that you create something like this file, where I told IFC Convert to extract only the walls of the building. Maybe you want to extract the walls, but also you need like the windows. Think of the things that are fully necessary to extract the information that we want. So like in order to form an enclosed room, we need not only the walls, but also like the floor, the ceiling, the windows, the door. So exactly which kinds of things you need depends on the model that you have chosen, because some might have like a ventilation ducts or something that encloses things in the top. So think of doing something like that and run IFC Convert to generate an OBJ file or maybe multiple OBJ files. And you can start from these files to run your code. So once you have your bunch of OBJ files or your single OBJ file, the idea is to load this into Nef Polyhedra inside Seagull. There are different ways to do this. The suggestion from us is to not do it directly, because if you have already looked at the CSG and Nef lesson in this course, you will see that the data structure for Nef Polyhedra is very complex. So you can do sort of an intermediate step, go from OBJ, load it into memory, and convert it into Seagull's Polyhedron tree. Polyhedron tree uses a half-edge data structure, which you are familiar with. And it's easy to create a polyhedron tree using this polyhedron incremental builder. The polyhedron incremental builder actually does basically what you did in homework number 1. So it takes a bunch of vertices and a bunch of faces where the vertices are defined by the coordinates and the faces are just indices of the vertices. And it creates the data structure for you. So this is already provided inside Seagull. Yeah, I will not go through the code snippets here, but basically you need to define a special kind of structure in C++. And this structure, you will need it to call it by with the vertices and faces. The polyhedron builder tree has some peculiar stuff or some limitations. The first one is that it doesn't like incompatible orientation, so you need to keep everything oriented in the same way. It doesn't matter if it's inverted or pointing outwards or pointing inwards, so left hand or right hand oriented. And yeah, so if you look at the OBJ files that are generated by IFC Convert, these look slightly different from the ones that you have seen before. So, first of all, there's this G marker. The G marker in OBJ is used for groups, and IFC Convert creates groups for every single object in the IFC file. Then you have the typical vertices that you know. IFC Convert also creates normals for each vertex. These are not too important. They also have a use MTL. This means reference to a material in the OBJ file. And IFC Convert creates these definitions for every shell of an object. So whenever you see use MTL, it means that you are starting a new shell of an object that was converted. Then after this use MTL, you will have the faces. These faces might look slightly strange to you because they come not only with the vertex index, but also they come with a normal. So the second number actually refers to the index of the vertex normal. You can just ignore this because these are not relevant for your homework assignment. So just focus on the first thing. So this face is made from vertex 11, vertex 8, and vertex 1. And yeah, then it starts sort of again. So there's like a G definition, so this means a new object. The object comes with its own vertices.
What's the S?
Shell. So in theory, it's possible to define shells in OBJ like this. But yeah, for some reason IFC Convert doesn't use that. It uses the materials to mark these different shells. Yeah, you don't need to create generic code that works with any kind of OBJ you find on the internet. It's fine if you just create something that works with the specific OBJ files that are created by IFC Convert, which are, yeah, slightly different. Yes?
You mentioned that this Polyhedron 3, it doesn't like inconsistently oriented faces.
Yes.
How do you check if a face of a how do you check if it's consistently oriented?
Okay, so let me this in a way that it's also visible from the stream. So the idea is that if you have, let's say, two triangles like this, and these are correctly oriented, so they follow the same orientation, when you reach the common edge, on one side you should be going like this, and on the other side you should be going like this. So for an edge that shares two vertices on different sides, you should always go like from A to B on one, and from B to A on the other. The same, because this is you can imagine this is actually in 3D. So these are adjacencies between individual faces of a surface that is in 3D. If this is two manifold, you will never have more than two faces for an edge, and for every edge, the vertices at its same points should be in the opposite orientation, in the opposite order. So let's say that this is, instead of A and B, this is 1 and 2. So if you look at an OBJ file, that says this is 3 and this is 4. If you find something that says 1, 2, then you should find 2, 1. You should never find 1, 2 and also 1, 2 in a different phase. That's how you can check that these are correctly oriented. And yeah, if you want to use the Polyhedron incremental builder and your IFC file has this sort of weirdly, well, badly oriented surfaces, you need to do the fixing. Hope that answers your question. Yeah, so trying to do. All right, and there's one more thing. So if you look at these phase definitions that are used in the OBJ files created by IFC Convert, they never repeat vertices. Instead, what you find in practice is that some of the vertices have exactly the same coordinates, but each index of the vertices is only used once. If you pass this to the incremental builder, it will not connect things together. So you need to have unique vertices for the Polyhedron incremental builder in SIGAL to work. Yeah, don't worry if you don't catch all of the details that I'm giving you. Everything is in the homework description. And yeah, so if you use the Polyhedron builder, then it's very, very easy to create a NEF polyhedron, because NEF polyhedron in SIGAL has a constructor that just takes a polyhedron and creates a NEF polyhedron from it. And this works as long as the polyhedron is closed, which means that it works whenever you have a polyhedron that completely encloses one surface. So if you have some sort of I don't know, polyhedron like a cube, and this one has a hole, let's say, in the upper face, so that there's no interior and exterior, this will not work with the Polyhedron incremental builder. You need to have something that is completely enclosed. In practice, this can also be checked by the face, by the vertices for the face. So this thing that I mentioned, that there's like a vertices should always be present like in opposite orientations. They should also just be present twice. So an edge from 1 to 2 should be present twice, once from 1 to 2 and once from 2 to 1. You should never have an edge that is only present once, because that means that it's on the edge of a hole, like this one here. Because it's only present on the face next to it, right? There's nothing on the other side. Yeah, so these are the two things that you need to check. Well, you don't need to do the checking yourself. There's a function called polyhedron is closed that checks this for you. So next, you have created a NEF polyhedron for every single object in a building. So for every single column, for every single wall, for every single slab, and so on. The idea is that you need to next join them together. If you have seen the CSG lesson, you will know that you can apply like Boolean point set operations. So you can apply unions between elements. So if you just apply union between the walls, you will end up with something that slowly encompasses like the whole building. This sounds very simple, but actually, very often in IFC files, you will have small gaps. Like I think in a previous lesson, I told you that there might be some space for ventilation. There might be some space between the, the walls are not exactly touching, but there's like a 1 millimeter separation or something. And then you will not be able to get a completely closed exterior and a completely closed interior. It will sort of leak into each other. So part of this process that you need to do in order to create this big net polyhedron of the entire building is to do some minor repairs. And these depend on the building that you're doing. You don't need to create something that works for every single case. So you can do some manual fixes. And for this, there are some suggestions. There's this 3D Minkowski sum package. This is not something that we discuss currently in the course, although maybe we should for next year. Yes?
Manually program it.
Yes, manually program it using the help of this Seagull package. So, yes? Oh, sorry. Okay, so yeah, if you're familiar with like mathematical morphology in 2D, the sort of thing that you do in image processing, you can imagine that with these sort of things, what you can do is that if you have, let's say, two walls and they are not exactly touching, you can sort of increase their size by a little bit using a kernel of a certain size. So let's say that there's this size of a kernel. And if we run it for the entire wall, we can sort of expand it a bit. And if we do it for the other wall, we do it too, until these two are touching. And that's how you can repair small holes between the buildings. But yeah, you can do it in whatever way you want. If you want to slowly shift vertices, if you want to round them up or down, it's okay if you do this sort of manual scripting work. Whatever works for your building is okay. But anyway, at the end you should have one big net polyhedron, so encompassing the entire building. This will have an exterior surface, the exterior of the building, and it will have a bunch of inner shells, and these will be the surfaces of the rooms.
This part you are using similar libraries?
Seagull only. If you want to use something else, check with me, maybe. But Seagull has a lot of machinery that you can use for this, so I would recommend you to have a look at the packages. And yeah, once you have this big net polyhedron, you need to extract the different surfaces from it. This sounds easier than it actually is because the net polyhedron structure is quite complex. So there's a bit of code here that you can use. If you're thinking of using like the same thing that we did before, like from net polyhedron to polyhedron and there to something else, it's not a good idea because these only work with simple buildings. So anything that has multiple shells doesn't work. And since we have multiple shells, like the exterior and the interior, this will not work correctly. There's a proposed solution here because Seagull has a couple of macros that are very useful. This one that is called Seagull for all volumes. And basically, if you put it there, it will run an operation for all of the volumes in your net polyhedron. And if you do this one, Seagull for all shells off, you can run a certain operation for every single shell of a volume that you select. Yeah, this is important because when you look at how net polyhedra works, let me open that. Let's say that you have these two things. So there's a square in space, and there's a cube in space with sort of an antenna poking out of it. If you model this with a net polyhedron, you will have two volumes. There's one volume that is inside the cube, And there's one volume that is outside of the cube and into space, the exterior. And you will have three shells. There's a shell for this square. There's a shell for the cube from the interior, and there's a shell for the cube from the exterior. So if you wanted to get something like give me the inner shell of the cube, sort of the thing that you need to do to extract the rooms, what you need to do is obtain a specific volume, so the volume being the cube, and then from that volume you extract the shell, which is sort of the inner shell of the cube. That's why this is a useful operation. There's a bunch of code here in order to help you to figure it out. But ideally, the important thing is that you should keep track of which shell is which. So don't lose track of which shell represents the exterior surface of the building and which represents like the interior, so the rooms. And at the same time as you're doing it, try to obtain the required semantics, because at the end you need to export a CityJSON file, and these have a certain number of things. So if it's you need to know if something is part of the floor or part of a wall or part of the ceiling, and if you are outside you need to know if it's part of the roof, part of the wall, part of the ground, and so on. And this is this is not too complex. You can use the location of things, or most importantly you can use the surface normal. So you know that if you are inside, the normal of the floor is pointing up, the normal of the wall is pointing sideways, the normal of the roof is pointing down, that sort of thing, right? So you already have functions to compute the normals. You have programmed them yourselves, but also there are functions in Seagull, and you're free to use them if you want. And you just classify the normals into whatever semantics you need to apply. And yeah, at the end, you need to write a CityJSON file. For this, please look at the specifications of CityJSON. Since we are asking you to write something with buildings and building rooms, you need to use CityJSON 1.1, because this is the new version of CityJSON that supports interior stuff. There are a couple of drawbacks about this. So actually, since this is very new, there are not many viewers that support this new CityJSON stuff. Stelios, the author of Ninja, promised me that he's going to have a look at adding these rooms, maybe today already. And if you have a Mac, and you can try my software as well, yeah, it works if you just go to the CityJSON file and you change manually the version number from 1.1 to 1.0, because 1.1 is not supported yet. But you should be able to see the actual rooms. Another option is to use CGIL to convert to OBJ. Yeah, I don't have a very good method figured out, so if you find out something, please let me know. Yeah, at the end of the process, you need to submit a few different things. Please just put them in a compressed file and submit them through the link. You need to submit the original IFC file that you chose to work with. So not the IFC open house, but something a little bit more complex, but not too complex. Your choice what to select. The intermediate OBJ file or files that you created using IFC convert. And the CityJSON file with the results of your conversion. Then you need to write a report just submit it as a PDF. Yeah, we expect no more than 15 pages for this. The shorter the better, but just explain to us like what are the steps that you did. I will go through this in a bit. You need to submit the source code that you wrote to do the assignment. It could be one file, it can be many files. And a short README file that tells me how to run your code. So if you need to run it with certain parameters in order to be able to generate the CityJSON file, put that in the README. Just tell me how to use it. Yeah, all the deliverables are explained here for the report. Yeah, here are the main things. So document the main steps. The main thing is also to be critical, like don't just explain to me like what I already explained to you now, and it's already in the website. So what is specific about the methodology that you chose to implement? Yeah, focus on high-level descriptions. Don't just explain your code like line by line. And it's also very important to sort of have a critical view of this. So we don't expect perfect results. Maybe you need to do something a bit hacky. You know that it's not fully working. There are things that could be done better. So just be honest. Describe the pros and cons of your method. What works well, what doesn't. Assess the quality of your results. Like we know that there's a limited time frame, so it's good if you know like what are the limitations of your method. Like this part works well, but this part doesn't work so well, and the performance of your code. So how long does it take for you to run this? Like, and if you wanted to take, like, I don't know, like a huge high-rise building, would this be a feasible method or not? If you wanted to run this like for an entire city, would this work or not? And yeah, use a small section of the report to tell us how the tasks were divided among the members of your team. It should be relatively equal, both in terms of complexity and in terms of workload. Yeah, and this is how it's going to be marked. So there's one sort of 3 point if you just follow all the rules that are explained here. There's 3 points for the quality of the report. So the clarity of your explanations, if you are thorough or not, if you are, if you tell us like what are the pros and the cons, if you are critical. There are 6 points for the quality of the results. So whether you decided to go for something that is complex enough, whether your conversion process works very well or not at all. Yeah, so there's 6 points for that, 3 points for the report, and one sort of 3 point by following all the rules of the assignment. Yeah, so as I mentioned before, there's no code skeleton. You're free to structure things in whatever way you like. That being said, if you need a bit of help, I know that some of you are not that comfortable with C++ yet, so just let me know or sit here in the lab. I will ask you how you're doing and we can discuss. One thing that I'm highly recommending you to do is that once you have done like the sort of the initial steps, so understood the assignment and maybe done some initial tests, yeah, talk to me, tell me what your strategy is, your ideas for solving the assignment, and I can tell if it's a good idea or not. Okay? Any questions? Okay, well, good luck with the assignment. Hugo is already here for questions about homework assignment number 2, which is due on Monday. And I'll stay here in case you have any questions about the lessons.